So thank you everyone for coming, in person and online. Today's talk will be given by, I'm probably butchering your name, so I apologize.
All right.
Dr. Emanuele Pulvirenti, also known as Lele. So, and he's going to talk on soft exosuits for astronauts, musculoskeletal health maintenance and rehabilitation. So space stuff, basically. Okay. And yeah, so the Digital Health Seminar Series is run by Mikhail, Matt, Emily, Sarah, me, and Emma. The whole goal of it is to try to develop some international interdisciplinary connections between academia, healthcare professionals, and industry. We have seminar series every 2 weeks, from 2 to 3, and the location varies, usually stuff. So some housekeeping. So if in person, please register your attendance with the tablets. The webinar will be recorded and made available online. For online attendees, please stay muted during the presentation. There'll be time for questions at the end. And use the Q&A functionality. The chat will put your hand up to raise a question. So just a tiny bit of our speaker. He is a research associate at the University of Bristol, working with Robotics. And he holds an MN in aerospace engineering, an MSc in robotics, and a PhD in the robotics and autonomous systems, all at the University of Bristol. So he loves Bristol, if you can't tell. He collaborated with various industrial and academic partners, including Foster and Partners, the University of Milan, and European Space Agency. And his research interests are preserving muscular and bone health in astronauts and terrestrial users through the use of soft exosuits and functional garments. And his work is related to translating the technology to revolutionize rehabilitation for patients, athletes, and individuals recovering from injury on Earth. And he can explain it much better than me, so here is our speaker.
Thank you for the introduction. Appreciate it. Yeah, thank you so much again for having me, and thank you for being here, both in person and online. So my name is Emanuele, go by Lele. I work at the Bristol Robotics Lab. I finished my PhD in December 2024, and then I started a job as a research associate that exact month. And now I'm a research associate within the Vivo Hub, which is a 5-year project between 5 universities in the UK, with the objective of helping develop a set of devices to help people maintain their independence when they're older and in later stages of life, basically. The talk today, I called it "To Still Boldly Go and Stay," because the idea is during my PhD, I worked for the development of a soft exosuit to help astronauts maintain the muscle mass in space. But I think that this kind of technology can also be applied on rehabilitation on Earth as well. And that's hence the title. I was trying to be clever with it, but hopefully it worked. So just to give a little bit of background, this is kind of the problem that I was trying to solve and I'm trying still to solve. So this is an astronaut coming back from the ISS after 198 days in space. And as you can see, even walking in a straight line doesn't really come easy to him. That's because his vestibular system is all messed up from being in microgravity for so long. But it's also because his muscle mass and his bone density have decreased considerably since the beginning of the mission. So again, all the stabilizers muscles are the first ones that go, hence why even walking in a straight line becomes quite difficult. So the challenge is twofold, in my opinion. So the first one is in space. Obviously in space, the main problem is that you have prolonged exposure to low gravity. So either hypergravity, which is lower gravity than Earth. So it can be zero gravity, but it can also be moon gravity or Mars gravity. In that case, because of the lack of axial loading, which we always have here on Earth, we start losing a lot of muscle mass and a lot of bone density. We're talking about 20% of muscle mass in the first month of stay in space. There are existing countermeasures, but they are quite bulky, they're very heavy, and they have shown like subject intervariability, which means they don't work the same for everyone. And the second aspect of this challenge is obviously on Earth. So on Earth, we have similar conditions to the lack of gravity, let's say. We have patients recovering from neurological injuries or even from orthopedic conditions. And they spend a lot of time trying to recover the muscle mass when these conditions basically get in the way of their daily life, right? And the rehabilitation procedures that we have in place are quite slow. And obviously the NHS is overwhelmed, which means not everyone has the same access to rehabilitation practices, which means all of these stuff will take ages before the patient goes back to pre-injury condition. So there is a need for solutions. Here I wrote wearable solutions, but really it can be anything. There's a need for solutions that offer control adaptive resistance without impairing natural movement, so that the user can recover even when they're at home, right? So we want to move the rehabilitation of the user from the physiotherapy practice to the home. Same way we would do with astronauts, right? Instead of just getting them to exercise 2 hours a day, just that, we will also have a solution that helps them maintain the muscle mass, even when they're doing like daily tasks, you know? And that's kind of the vision. So again, coming back to space, just because obviously it's been my main stream of work, the vision was to basically create a device, a wearable device, with artificial muscles on top that could help the astronaut maintain their muscle mass throughout the whole stages of the mission. So obviously we would have the pre-flight training. We can use the device to help and enhance the training of the astronaut before the mission. And we could also use during the mission, during the transfer in microgravity, for example, while they're exercising, we enhance that exercise by using a soft wearable exosuit that puts resistance onto their body. Same goes for later stages of the mission. So for example, when we get to the moon, let's say, we're doing our extravehicular activities, so our science exploration and all that stuff. We could have the astronauts wear the suit underneath the spacesuit and compensate for the effect of low gravity. In that case, there's also another aspect. We could use the suit to be assistive, because heavy spacesuits basically limit your mobility quite a lot, which means it could help in that case actually to have a little bit of assistance to regain that mobility. But I'll get back to this in a bit. And then obviously we have the post-flight. Ideally the astronaut would return on Earth with preserved muscle mass. But there's also the case where we could use the device to help them to recover muscle mass faster. Usually astronauts take about 3 to 6 months to return to pre-flight conditions, and this could reduce those recovery times. I don't know about how much because I haven't tested it, but it could. Ideally, it could. So just talking about the device that I developed during my PhD, I call it the RX suit, which is the resistive hypergravity exosuit. It was the first resistive exosuit designed that I'm aware of. So all the exosuits that have been developed so far in the literature are all assistive, so they're all meant to help people with their mobility. This one is the first one that actually makes it harder for you. So I don't know how good it is actually, but but yeah, basically what it does is that it applies resistance to your walking. So I'll explain a little bit later how it works, but it's got sensors that tell you when in the gait cycle you'll apply the resistance. It's very lightweight, it's about 1.4 kilos. And when we compare it to existing exoskeletons, so rigid exoskeletons, we're talking about 26, 27 kilos of weight. So we're working at a fraction of that, basically. And then it's highly cost effective. Developing this cost me about 800, 900 pounds without counting the endless hours spent on my sewing machine by myself, obviously. But it is highly cost effective. When we look at existing exoskeletons, we're talking about 75 to 90k pounds. So that's their commercial retail price. So, you know, again, we're working at a fraction of existing solutions. The exosuit itself is powered by these soft artificial muscles, they're pneumatic. We call them bubble artificial muscles, and you can probably understand why we call them bubble artificial muscles. The way they work is that they're made of a tube of inextensible material. In this case, it's plastic. The newer version are made of fabric, so they're quite easily integratable in existing clothes. You divide this tube in sections by using stainless steel rings, and the rings, once the air goes in, basically limit the radial expansion of the material and creates these little contractile units that you see here that behave almost exactly like a biological muscle. So the force and the contraction that we get out of them are very comparable to what we get from our biological muscle. And again, they're pneumatic, so they're extremely lightweight. So one of these weighs about 100 grams, and it can develop up to 100 newtons of force. So they're quite good, and they're very easily manufacturable as well. Before going into the actual device, I did some work with trying to understand how we could input forces onto the human body. So what I designed was a robotic leg, I guess. So what you see here is a rig that simulates a swinging leg. So imagine the thigh is fixed, and then the only thing that's going is the shank, so the lower leg is swinging. It's controlled by an electric motor at the back and everything, and it's got a gravity compensation algorithm. So what we did is basically we simulated low gravity, the leg swinging in low gravity, to understand how we could input force into a swinging leg by using these artificial muscles. The ones that you see here are the ones made of fabric, actually. So the important thing that came out of this is, okay, we know that the BAMs, the bubble artificial muscles, can develop the force that we need to perform assistance. But also what we found out was that they weren't influencing the frequency of walking. So, usually when you wear something, it will influence the way you walk. We managed to deliver force onto the human body, well, onto the robotic body in this case, by not influencing the walking frequency. And that is a huge thing because you want these devices to be as seamless as possible, right? And then in the last part of my PhD, I moved on to my the device development. And you can see from this video, this is a video from the tests that we did in Milan. The way it works, it's got two sets of actuators, one at the front and one at the back. The front actuators resist the flexion of the leg, whereas the back actuator resists extension of the leg. So this is very interesting. The way we tested this was in a European Space Agency ground-based facility. Basically, the way it works, it's a 17-meter tall elevator shaft, like an old empty elevator shaft. And they have a set of bungee jumping cords coming down from the ceiling, sorry. And then they put this climbing harness on you, and then you're just hanging on from these bungee jumping cords. And then they can simulate anything between Earth gravity to moon gravity by just sustaining a portion of your weight. And it actually feels like you're walking on the moon, which is pretty cool. So we tested this in Milan, and we tested it both in Earth gravity and in moon gravity to understand what the effect of the suit would be in different gravity conditions. And we tested it with 6 people. So not a massive sample size. And for you guys that do data, you'd probably kill me, but I did statistics on it. So, it works. So again, this piece of work was basically the main piece of work on my PhD. And here is just a summary of the results. Again, we were delivering resistance to walking, right? Because walking is quite a periodic motion, so it's quite predictable. But obviously, we can think about in the future about other activities to resist. But anyway, during walking, what we noticed is that the metabolic expense, which is basically how much energy you're using during walking, we were able to bring the metabolic expense to Earth levels when wearing the suit in a resistive mode. And then our muscle activation data as well increased. So we got the rectus femoris, which is your main knee extensor, and then you've got your bicep femoris, which is your main knee flexor. So by measuring EMG activity of these muscles, we noticed that by wearing the suit in a resistive mode, we were able to even increase and surpass the muscle activation of these muscles on Earth. So this is kind of an initial lead into what the suit could do in the long term. Obviously, we haven't done any long-term studies. But again, just looking at the detail of it, I'm not going to bore you with this. but you can see I did start with this. You can see that, you know, when you walk on the moon without wearing the suit, your metabolic expense goes down compared to Earth without the suit, goes down by quite a bit. Wearing the suit in the active mode, so by adding active resistance to the body, we were able to bring this metabolic expense back up and even more than we usually see on Earth. The metabolic expense is just a general measure of how much your muscles are working. So it tells us that your muscles are working more, but by looking at the EMG activity specifically of certain muscles, then we were able to tell which muscles are working more than others. And we saw that all of the knee extensors and knee flexors were working more than they would when they were on Earth by wearing the suit resistant mode again. And then we saw some weird stuff happening with the lower leg muscles, but those weren't the target of our device in this case. But what that told us is that maybe we need to look at multi-joint soft exosuits. So not just one joint, not just the knee, maybe the hip as well and the ankle, if we're looking at walking specifically. So, you know, again, it's not a final solution, and I'm not claiming that this is going to maintain muscle health in astronauts, but it definitely gives us a lead to where, what to look at and where the device development should be going. And again, one of the major things that I found was that these devices cannot influence the way you move, okay? They need to feel seamless. They need to feel like wearing a pair of trousers, exactly. And so what we found was this was interesting. Even when we wore the suit with resistance, the way you walked didn't change. We looked at walking frequency, we looked at joint kinematics, so all the joint angles that we needed, and they didn't change at all. So this was quite important, because then we proved that we can make basically an active pair of trousers that doesn't really influence the way you walk and the way you move. So moving on from this, moving on to a little bit of current work, and I'd say this is one of the coolest things I've ever done in my life, to be honest. So when we were talking about the stages of the mission earlier, we were saying this kind of suit could be used for enhanced mobility when you're wearing a spacesuit. And that's actually what we tried to do. So I met someone at a conference that still is the CTO of a company that does analog space missions. So they basically pretend to be in space. They go in the middle of the desert for like 3 weeks, and then they're like, "Oh, we're on Mars," you know. But it is, so I make it sound stupid, but it's not. It's really very realistic. They have a whole thing going on. But basically, the problem that we were trying to solve was this. So these are videos from the Apollo missions. And these are astronauts just trying to move around on the moon, and they can't, you know. So this has to do a lot with the lower gravity, obviously, but it also has to do with the fact that the spacesuit that they're wearing doesn't allow them to move properly. So their mobility is extremely limited. A lot of astronauts, even with modern spacesuits, a lot of astronauts have complained about injuries and like just general discomfort, especially their knees, their shoulders. And this is terrible, right? Because if we want to go to the moon again, or we want to go to Mars and like start creating our own habitats and doing our own science, we can't be doing this all the whole time, right? It's terrible. And this actually has caused a lot of injuries in astronauts. So imagine you're on Mars, right? There's no physiotherapy practices, there's no hospitals, there's nothing on there. If you fall like that and you break, I don't know, your leg or your knee, or you injure yourself, it's going to be a pain, right? So what we tried to do with IC Space, which is this company that does analog space mission, we tried to basically test a assistive version of the exosuit to fit within their analog spacesuit. So IC Space, they have their own spacesuit. It's a simulated spacesuit, so it's not fully pressurized, but it does simulate a lot of the constraints that a real spacesuit has. And so what we designed, you can see here, it's another version of the exosuit, this time to help astronauts move while they're wearing the spacesuit. This one, it assists knee extension and ankle plantar flexion. So basically, it assists this motion and also this motion. So when you're trying to push up, that's the motion that it assists. And that's because most astronauts, when they wear a spacesuit, they basically walk like this, like a crouch-like gait. So they don't have much knee extension. They can't really push up well their foot, which means maybe the hypothesis was maybe if we have a soft exosuit underneath the spacesuit, we could help them with those motions. So we went to Australia for 3 weeks. We were working with the University of Adelaide, and they have one of the biggest, actually the biggest lunar simulants in the southern hemisphere. So it was basically a room filled with lunar regolith, it's called. So it's like lunar soil. It's simulated, obviously, it's not actually from the moon, but it's very realistic. So we put 4 astronauts inside this for 2 weeks, and we gave them some wet wipes and a camping toilet, and that was it. But basically, what they were trying to simulate was isolation, right? So the main aspect of a space mission is that these people are going to be in isolation for months, years on end, right? So they were trying to understand that kind of side of things, but they were also doing extravehicular activities twice a day. So twice a day, they would suit up with a spacesuit and go do stuff on the lunar surface. And that's when we tested the exosuit. So we gave them the exosuit, we gave them the system, and we were like, okay, with the analog spacesuit, you need to test also wearing the exosuit and see how it works. And so, yeah, we did some field test. This was the first time we took it outside of the lab. The really interesting thing was that the terrain is uneven, it's not earth terrain, it's not flat, and plus you have the analog spacesuit on top, which means the level of unknowns, it's just so much higher than when you're at the lab. It was a critical validation step for mobility, comfort, and force transmission during EVA tasks. But the main thing was that we were able to test it with the people that are actually going to use it, right? These are the potential end users of this technology, and they gave us some really good feedback, like even just comfort-wise. If it's something that they just can't wear for too long, it's useless, right? So you need to look at that aspect as well, which is something that as engineers, we often don't think about. This is more like what designers do. Which is why this is interesting, because this was like a project between human physiology, designing, and engineering. And it showed me that I really don't know what I'm doing sometimes, but it was interesting because it's a lot of exploratory stuff, right? You need to think about this stuff needs to integrate with the spacesuit, which is something that's external, right? Which could translate really well on Earth as well, because people are not going to want to wear a suit like this just out and about, right? So they might want to put their clothes on top of it, which means you need to understand the interactions between 2 different systems. So moving on to the slightly cooler stuff. This is the first video of the first extravehicular activity with the exosuit on. So you can see that astronaut is wearing the exosuit underneath the spacesuit. And they're doing 3 tasks here. The first one is just level walking, so just like forwards and backwards. This one was incline walking, so we basically asked them to go up an incline and down an incline. And then they also did a load bearing task, so they had a 10-kilo bag with them and just try to understand how that works. And then there's a close-up video of them as well. So this is just, again, this is the load bearing task. So the same astronauts are doing the load bearing task. And you can't see the exosuit, but it is underneath. And it's at the moment it's still tethered. But this was the first time that we actually didn't do it on a treadmill. It was pretty cool. So these are just some preliminary results. I'm working on the paper now. But you can see it's not very clear in this figure, but you can see that when we have the exosuit on, which is, these blue, green, and purple lines, You can see that these are muscle activation data. So this is how much your muscles are working during walking. And you can see that here, for example, we have a much lower muscle activation than we do without the exosuit. And the same goes for this one. And the same goes for this one and this one, which means, so most of them, all of them are, these three are knee extensors. So the knee extensor less, which is the ones we're targeting. And also we have the GM that's working less. The GM is just your calf, basically. And the calf is also working less because of the actuator of the artificial muscles that we have on the ankle. So this is just, again, it's a very preliminary conclusion that we're drawing, but basically what it does, it's your muscle activation is decreasing, which means you're using less energy, which means it's being less uncomfortable to wear the spacesuit. So we had a lot of interest on the exosuit. So obviously when people hear space and when people hear astronauts, they're like, oh, this is so cool, you know. And obviously I'm not bringing up this slide just to boast how much like people have talked about it, but what a lot of people ask me about this stuff is that they were really interested in the technology itself rather than the application. And it just shows that this kind of stuff does have potential to help people later on in the future, and that there could be applications for us rehabilitation as well. So talking about a bit of, finally, just to conclude as well, I'm thinking of bringing this to higher technology readiness level. So for now, I don't know if you guys are familiar with the TRL concept. But basically, at the moment, on a scale of 1 to 9, my suit is 4 to 5 ready to hit the market and to be used by astronauts. So there's a lot of stuff that needs to be done before that happens. And I could bore you with the details, but the main thing is that we need to look at those medium-term to long-term studies, you know. We need to understand what actually wearing this suit would do to someone if they wore it for 3 to 4 months, basically. Because we don't know yet, right? We've done very brief studies and short-term studies. So we don't know what physiologically wearing this kind of device will do to someone. And then obviously to get it on into space, that's another story. You need to do all the kind of like quality control on the software, the hardware. It needs to be fully ready to be tested by real astronauts in space. So just talking about some related work as well, I've not just done exosuits. I've worked a little bit on fundamental stuff. And this is one of the works that I really, really liked, and it was scalable bubble artificial muscles and also atomic packing of artificial muscles. So one question that I asked myself is, you know, these artificial muscles, I haven't brought them with me today, but they're small, but they're bulky, right? When they inflate, they're little bubbles of air, right? So you don't really want that on your trousers, right? So the question was, how small can we make them while still getting the same performance out of them? And this is kind of the work where we realize that if we make them bigger, they're not going to perform necessarily better. So we didn't go to the smaller scale, we went to the bigger scale to say, okay, first we need to confirm that if we make them bigger, they're not going to work the same. And this is actually what we found. So from this figure, you can see that having 3 small bands, so 3 small bubble artificial muscles, will create more tensile force than having 1 big one. And what that does as well is that it saves on half of the volume that's needed. So you're basically saying, okay, the smaller we go, the less volume we use, depending on how they're packed, we can get better performance out of them. And then we looked at packing them. So we said, okay, how can we put them in an efficient configuration so that we get the performance that we need? And I think the best packed things in the universe are molecules. And when you look at crystalline structure of molecules, they have different packing configurations. So there's like face center cubic, body center cubic, hexagonal closed pack. Anyway, there's like this whole thing. And I've never been good at chemistry or, you know, physics, but they were quite interesting. And so I was like, why don't we try and pack them like atoms are packed in molecules? And what we found is the different configurations give us different performances. So if we want really high force, so really high stress, for example, you go for a face center cubic configuration. Whereas if you want high contraction, so you want high stroke, you go for a body center cubic configuration. So this might not mean much, but it basically means that in the future, if we can make them to a muscle fiber level, so to a muscle fiber scale, then we can pack them in certain ways to get the performance that we need.
Can I ask?
Yeah, of course.
Was this orange ring necessary for those, or
That's just to keep them together.
but would it be necessary then in case if
Probably not. You can solder them on top of stuff, and yeah, because this was just for a tensile tester. So yeah. And then the other piece of work that I did during my PhD and also during my postdoc was with a architecture studio in London, Foster and Partners. And what we were working on was something really cool that I wish I had more time to talk about. But basically, we work a lot with metamaterials, auxetic materials. So these are materials that don't behave as materials in nature do. So when you pull on a piece of let's say plastic, for example. If you pull on a piece of plastic, it will contract. Whereas with a metamaterial, with an auxetic material, if you pull on it, it will expand. It's like that ball that we had as kids, as a toy. I don't know if you guys have seen. Anyway, the really cool thing about auxetic materials is that they also have the same plastic curvature. So instead of curving this way, they curve this way. And what that means is that they really adapt really well to the curvature of the human body, which is not like the human body, the human arm, for example, is not just a cylinder. It's a very complex curved surface. And one of the main things that we were trying to solve here was anchoring. So on soft exosuits, because they're soft, they don't really anchor well to the body. So we were trying to find new ways of basically attaching the actuators to the body in a way that maintain comfort, fit, and security of the anchoring. And auxetic materials really helped with that. It's a project that we would have liked to continue, but the European Space Agency, I mean, they gave us the funding, but with really weird conditions. So we're like, you know what, guys, it's fine. Like, we don't need to do this right now. But yeah, if you have questions about this, I can talk about it more. It's really interesting. And then again, just to conclude, future avenues. There's a few things on the fabrication side and also on the physiological and device development side. We want to develop consistent ways of creating bubble artificial muscle. At the moment, it's just me in the lab making them by hand. And I have to be honest, the quality is not the best, you know, it could be much better. And then obviously miniaturization. So we want to get these bubble artificial muscles or generally artificial muscles to a, you know, muscle fiber scale so that we can fabricate them really small, but we can get the same performance out of them, like I was saying before. And then adaptive control. So we want these things to be controlled the same way muscles are controlled by the nervous system, for example. And this is on the improvement of the actuation technologies. And then we have the design of future spacesuits and actually like seeing like device development. There's a lot of stuff here. So low transmission, like the links to the anchoring problem that I was talking about. Soft exosuits are way too soft. So when the actuator pulls on it, it's like if I pulled my pants down all the time. So I need an anchoring that actually provides secure fit. We want to make them portable. At the moment, there's a big elephant in the room that I haven't talked about, and it's a 50 kilo compressor at the back of the room that we use to, you know, put air into it. So we want to try and create different ways of supplying air to these things. And then also long-term testing, which is something that we really need to look at before we make any conclusions on the effects of these devices on humans. And then, yeah, this is a short video about the Vivo Hub, which is the project I'm part of. I'm just going to let the boys.
Longer. Personalized working tool for extra strength and symmetry. Smart lenses for rehabilitation. Keeping outbound muscles and bones healthy. Even it's staying.
So basically, this is just a very short introduction about the Vivo Hub. What the Vivo Hub objective in the next 4 years is to develop a series of devices that we can use with people here on Earth to help them maintain their independence for longer. So we don't want people to never die. Well, technically you do, but you know that we can't do that just yet. But we want to maintain their health as stable as possible in later stages of life, right? So at the moment, for some people, even going out to the shops becomes quite hard because they don't have the mobility for it. But we could develop, well, we want to develop a series of devices that could help them with that. And like linking back to our discussion before as well, there's a lot of stuff on fall prevention. So we want to look at markers, physiological markers, or even markers coming from the sensors on the suit that could tell us when someone's falling. So falling is one of the main causes of injury in the UK for older people, and it overwhelms the NHS really. So having a solution for that in the form of a device that you can wear every day could really make a difference. And this is kind of what the Vivo Hub is doing. So we're working a lot with actually digital health people. So we have Telmo that's working with us, and we're going to do some work at the Sphere House as well next week. Actually, if you guys want to be subjects, that would be great. So yeah, there's a lot of stuff that we're going to do within the Vivo Hub. And again, if you guys have any questions about that, please let me know. And this is how I conclude my talk. So just a little bit of background on the pictures. I always put this at the end of my talks. It's a pale blue dot, and it was taken by Voyager 1 on Valentine's Day in 1990. And this is Earth 6 billion kilometers away. Basically, it just reminds me that whatever we're doing for space, when I love space and I love the idea of exploring space and everything else. But whatever we're doing it for home, right? This is the only thing we have left and we've ever had. So I don't know. I just really like this picture, and I just hope that conveys the message. Anyway, thank you so much for listening to me.
Thank you for the great talk, Lele.
Thanks.
So let's have a round of questions. First, we'll do questions in person, then we'll go to online if there's any questions.
Yeah.
Yeah.
I don't know anything about soft robotics.
That's nice.
But we were slightly joking about people of very different heights being astronauts at that time.
Yeah.
Wrong to think that I'm too short to be an astronaut. Is there any change in efficacy based on the length of each of those muscle imitating units?
Yeah.
So someone whose legs are 2.5 feet long compared to 3 feet legs.
Yeah. So this is actually a great question. So both the devices that you've seen, I've designed them in a way that they could be adapted for different leg lengths. So they cover between the 5% and the 95% of the scale, basically. So I've tested it with a couple of people that were what I'm guessing is your height. So they were both women and they were short. Sorry. Shorter than me. Let's put it this way. And it worked really well anyway. So obviously there's a few tweaks that you need to do. So like I said, my device is designed so that it can be regulated. But I think in the future, I mean, my ideal would be a one-size-fits-all device. So something that can adapt to the shape of your body and to your height and to your limb segments. But I think more realistically, you just have to have different sizes. But no, it has been shown to be effective even in people that are less tall. Yeah. Yeah.
Okay, then I'll ask a question.
Please.
So right now, these suits of like people going to space and stuff, right? Would there be any like possibility to have a suit like this for someone on Earth, like particularly like the resistive kind? Like, because a lot of people like go rocking with like weighted vests and stuff like that.
Yeah.
Could I potentially use a spacesuit or an Earth version of a spacesuit to help me add some extra load to me with like distribute everywhere?
Yeah. So ideally, I mean, I haven't really touched upon it, but you could use this technology with athletes as well. So a lot of athletes could be using a resistive suit to enhance their training. The same way you enhance astronauts training, basically, Again, the devices that you've seen are designed for walking. So there's not really much you can do with that, but you can design a device for, I don't know, resisting a squat or a deadlift or that kind of stuff, you know, or even running or, you know, all the activities that like rugby players do for impact. Again, it's mostly a design challenge in the sense that you need to design a device specifically for that at the moment. But again, in my view, we could make a device that does everything. So a device that basically knows what the activity that it's been done is and activates depending on what you're doing. So right now we're working on a version of the suit that switches between resisting and assisting. So it knows when it needs to assist, it knows when it needs to resist. And so that's a first version of a all doing suit, right? But you could definitely have a suit to help athletes and then rehabilitation as well.
I find it a bit of a contradiction that you focus, or as part of it, focus on astronauts, which is one of the most expensive things that people will invest in to ensure the safety of the astronaut.
Yeah.
And at the same time, you are proposing a product that is 100 times cheaper than other exosuits, which it sounds a bit strange to me. Like,
it's too good to be true.
Yeah. If they have the money, why don't make the most expensive stuff, but that it's reliable, rather than trying to be cheap on the product somehow? No.
Yeah.
I don't know. Yeah, I find it strange.
No. I completely understand. So I mean, if you look at the way the space industry is going, so about 10 years ago, a launch would be $130 million, right? One launch. Now we're talking about 80, 70 million. And it's because, for example, people, you know, players like SpaceX have come up with reusable launches. So in space, whatever you can do to reduce the cost per kilo of payload. So that's the big measure. Cost per kilo of payload is what everyone wants to reduce.
Yeah.
So if my cost per kilo is $100 per kilo of payload sent, and in 2 years it will be 75, that's a 25% saving on my side. It means I can send more payload.
Yeah.
Right. So when we look at a technology like this, not only it's more effective than a rigid exoskeleton in maintaining your muscle mass, it could be, but it's also lighter, which means you can send more payload, right? If I can send more oxygen, even 3 kilos additionally of oxygen, then it's a win, right? So I don't think it's a matter of choosing the cheapest option, is what really makes it more affordable in terms of like payload wise that you can send, right? The fact that it costs a fraction of what the actual devices cost, it's not a measure of how effective it could be, right? So if they can save money, why not?
Yeah.
Does that make sense?
Yeah, of course.
Yeah.
I just wondered how you saw it, because I guess this is the work you do with Depot, how this would translate to resistive exercise and training, like rehabilitation for people with like musculoskeletal conditions. And kind of how that would compare to existing methods of resistive training, like things like hydrotherapy. And how it is, you know, is it the kind of more targeted, adaptive nature of this that makes it more suited to those things? I wondered that.
So I can't answer you with data because I haven't done the comparison, right? So I'm just gonna speculate here. But so for example, when people that have had the ACL injuries, the first thing that they do is resistive training. So straight after operation, they do resistive training, and that's very targeted resistive training. So we're talking about proper like leg extensions, leg curls, like that kind of stuff. The problem at the moment, especially for people that aren't athletes, so if I get injured and I tear my ACL, I have to go into an NHS hospital. I have to get my operation, whatever, and my physiotherapy will be paid for by the NHS, but it's very limited. So the access to physiotherapy through the NHS is extremely limited. the idea is if you can have a device that you can take with you at home, it doesn't cost much, it doesn't weigh much, and it doesn't limit your mobility, then you can do your resistive training while you're doing other things, right? If I just have, for example, if I'm walking around and I'm recovering from an injury and I could benefit from a little bit of resistance, then the device could be able to give me that even without me walking into the physiotherapy practice. Obviously, we have to look at other things as well. So if we're talking about neuromuscular conditions, a lot of people might benefit from assistance at the beginning, but then that you don't want to make them too reliant on the assistance. Because if you keep assisting them, their muscle mass will reduce and it's not going to be beneficial for them, right? So you want a device that maybe in the first phases of rehabilitation, it assists you to regain a little bit of mobility, but at the same time, as you get more mobile, you get more resistance added so that your muscle mass is maintained. Again, in these cases, we're talking about sub-maximal resistance, so it's not like when you go to the gym and you go to failure, right? It would be a load that it's important input on your body throughout the day, right? And it's something that otherwise you wouldn't have, right? So it could, again, basically improve the amount of time that you need to rehabilitate from certain conditions. Yeah, does that?
Yeah.
I don't know how it compares to other. So, for example, hydrotherapy is really good for older people because it's very gentle on their joints. So it's not like gym resistive training. Some people can't do that. I don't know how it would compare to that kind of thing. But again, it's mostly an accessibility kind of thing, Like to do hydrotherapy, you have to go into the facility. Exactly. Yeah.
And in space,
exactly. Right. So imagine the vision is having a device that you wear like a pair of trousers and you use it throughout your day and you don't even notice it. It's very ideal, very idyllic, but it could work.
I've seen other actuators that use pumped air, like to move like kind of syringes or things like that, which would make something similar, no? But is it the difference? Is the main difference only on that in your case the bubbles are soft and the other one would be rigid, or are there other differences?
You can have pneumatic pistons, which I'm guessing is what you're
probably
thinking of. So like syringes, you can drive syringes with air, and they produce a lot of force. But the main thing is the rigidity and the weight
that will be the
of
main.
them. And these actuators that we use again are made of fabric, which means I can just sew them on top of a pair of trousers. And they would be seamlessly integrated in the clothing. So what we're trying to make is smart robotic clothing that doesn't look like an exoskeleton, like it just looks like a cool piece of fashion, really. One of my dreams is to have my exosuit at the Milan Fashion Week, and just see how cool it is. But it's mostly that, like rigidity, weight, and how cumbersome it is. So if it limits my mobility, if it's just too bulky, I don't really need that,
So you're talking about the packing of the artificial bubbles and stuff.
Yeah.
And that was based on inspiration from like molecules.
Yeah.
Would they be able to get any inspiration from like the air sacs in our body, like alveoli and stuff like that? Because it doesn't have like a really high surface area and stuff.
That is really interesting. I don't know. It could be really good. I'm not sure how they're packed, but there are a lot of things in the universe that are packed for maximizing surface area and performance, and they're really, really efficient. Like for example, when you look at ants nests, like ant colonies, they're so intricate, but they maximize the amount of space that they have. The same goes with bees, right? They're, what are they called? I can't remember what they're called. Hives. Yes, beehives. They're extremely efficient and they're optimized for airflow. So, and they don't know that they're doing that, which is crazy. So there's a lot of this stuff that you could look at to see packing configurations and how they're going to be packed. But we have to remember in this case, we have to put them on the human body, right? So it needs to be something that we can use on the human body, right? Obviously, when we go down to like microscopic scale, so like muscle fiber scale, then we could play around with those concepts. But yeah, thanks for the idea. I'll put your name.
Yeah, that's fine.
Yeah.
One more question from me, quick
Yeah.
one. So when people go into space, how is gravity in like the spaceship and stuff like that?
Yeah.
How I'm saying like, is it
So, for
gravity at
example,
all?
when you go into the International Space Station, there's no gravity. So it's microgravity, they call it.
Okay.
So because you're constantly going around the Earth, and it's like you're basically constantly free falling.
Okay.
So that's why you feel zero gravity. On the moon, the gravity is 16% of Earth's gravity, and on Mars it's 38%. So it's very low, which means, I mean, our bodies are designed, but they're not designed, but they're adapted to Earth's gravity. Which means the moment you go into a lower gravity environment, your muscle mass will go down, your bone density will go down. And then there's another thing which is terrible, which is the fluid shift. So because there's no gravity, your blood is not going down to your legs. So it basically stays all up here. And this is why you get a massive heart, and risks of heart attacks increase. You don't get as much blood flow, so you get blood clots. So if you care about your body, don't go to space, because everything is trying to kill you. Yeah.
And
Yeah.
I've seen those simulations of no gravity, that it's basically going into a plane and free fall, and that's a simulation of no gravity. Is there something similar as well for different levels of gravity? Like you say that the moon is 16%.
Yeah.
Do they do that?
So-
like falling at a certain speed or things like that?
Yeah. So they're called the parabolic flights. Or actually, in more informal language, they're called vomit comets, because they're disgusting. Like, it really makes you nauseous. It's terrible. They have to give you medications before you go into those. But basically, yeah, what they do is 5 parabolas. So they go up and then they go down and they go up and then go down again. Depending on the angle at which you go down, they can simulate a different type of gravity.
Okay.
So if you go down,
Yeah.
like proper down, that's like zero gravity.
Yeah.
But then if you increase the angle of the parabola, you get a different gravity. So I have a colleague in Milan, actually the guy that I work with, and he did a campaign on a parabolic flight just last month, and they did moon gravity.
Oh, yeah, that's what I was
Yeah,
wondering.
yeah.
If they could simulate how walking on the moon on those circumstances.
Yeah,
would
they
be.
can.
But probably there is not much time to.
No, it's very short. So the down parabola is like 30 seconds. So you only get 30 seconds of data, which is not much, especially when you're doing human studies. Like my stats is already questionable here. So imagine if I only had 30 seconds of data, you know? So, and then changing subjects within the flight is quite hard, you know, the space is quite limited. Yeah, but they are pretty cool. They do a lot of stuff on those. In this campaign that this guy went into, they were just trying to understand how you could jump on the moon. And then there was other stuff like a moon gravity 3D printer, that kind of stuff. You know?
Is there anything with like hypergravity, extra weight, like, do you know, like Goku training or something?
The only thing I know that does hypergravity is the centrifuge the astronauts use for training. So they just put you in this, like, it's literally centrifuge, and they make you pull like 7-8 Gs, and everyone passes out. But it's where you pass out. If you pass out at like, I think the limit is like 7 Gs. If you pass out at 7 G, you can become an astronaut. If you pass out before, you're basically garbage. Yeah.
I think it's true.
Any more questions, sir?
How do you plan on getting 12 weeks of test data?
So basically, there's a guy I know that works at the European Space Agency. He works at the European Astronaut Center, and sometimes they do bed rest studies, which means you basically put a couple of astronauts in bed for 3 months, and that simulates low gravity basically. So what I want to do is a bed rest campaign where I put like 3 astronauts in bed, and then 3 times a week I make them do exercise. One of them does it without the suit, and one of them does it with the suit, and I see what the effect is. But yeah, it's bed rest, which means you need to recruit astronauts and tell them that they're going to be in bed for 3 months. It's not ideal, and like they've done it in the past. They have done it in the past, and
it sounds to me like the ethics to approve that would be.
you know, when you become an astronaut, there's nothing that you can't agree to. You know, the experiments that they do on astronauts are terrible. You know, so yeah, no, but they do that. So I think that's the closest I can get to a like medium term study, basically. Yeah, I wouldn't want to do it myself though.
Any questions online?
No questions online.
Cool.
Yeah.
Okay, then let's thank Dr. once again. Great.